Hello everyone, welcome to topic 3.11, spectroscopy in the electromagnetic spectrum. In this, you should be able to explain the relationship between a region of the electromagnetic spectrum and the types of molecular or electronic transitions associated with that region. In that, we are going to begin. So pay attention to the types, so microwave, infrared, and ultraviolet, and the types of transitions that you should expect to see. So spectroscopy is the study of how matter interacts with the electromagnetic spectrum. The electromagnetic radiation is classified into different types based on the wavelength or frequency of the radiation. So this graph or figure should be familiar to you, in that we looked at this in our first year of chemistry. We start off with short wavelength and higher energy light waves, so gamma rays. And then as you move to the right, you end up hitting radio waves with longer wavelengths, lower frequency, and thus lower energy. And in the middle, very small amount, is the visible light, the actual light that we can see. So molecular movement, molecules can move in different ways. These can be categorized as translational, movement from one place to another, rotational, spinning in one place, and vibrational, moving in place, the movement of atoms within the molecule relative to one another, such as bending, stretching, and other internal movements within the molecule. And so here we have an example of each. So the different vibrational movements where we have asymmetrical, symmetrical, and then stretchings, and then we have bending. And then we have rotational movement where they spin on one axis or another. And then translational movement where they move in a straight line, kind of like gases. So microwave rotational spectroscopy. Microwave radiation is lower in energy than visible light. When the microwave radiation strikes the particles, it causes them to rotate. This is due to the interaction of the dipole of molecules, even temporary dipoles, interacting with the electromagnetic field of the microwave photons. So it's kind of like charged particles interacting. The magnetic field generated by microwaves causes them to rotate. Infrared vibrational spectroscopy, or IR spectroscopy, is higher in energy than microwaves but less than visible light. IR spectroscopy measures the vibration of the atoms and allows the determination of functional groups. That's like alcohol groups, CH groups, CO groups. This is highly useful in organic chemistry. So this analyzes the absorption, emission, and reflection of different functional groups. Generally, lighter atoms and stronger bonds tend to vibrate at higher frequencies, where we see that over here. Okay, and so there's different types where you would find, so along the x-axis, where you would find that functional group and how big it should show. So strong, broad indicates that the OH group has a very low, based off of how we're reading it, but a very steep peak, but it also is spread out. Okay. You do not need to memorize these. This is just to give you perspective on what it's talking about. So type of bond is the functional group. This is where the peak would be located, the wave number, and then the intensity is describing the type of peak or the shape of the peak. And then ultraviolet or visible light. This is also called UV-vis for ultraviolet visible spectroscopy. Visible light spectroscopy is concerned with the part of the electromagnetic spectrum that we can see, the colors in the rainbow, the continuum from red to violet, from low to high energy, which is about 400 to 700 nanometers. The ultraviolet portion of the electromagnetic spectrum is higher in energy as the wavelengths are shorter, about 500 to 400 nanometers, and therefore the frequency is higher. The interactions of these wavelengths of the electromagnetic spectrum and molecules or atoms can allow for the determination of the concentration of the molecules in a solution. The photons of colored light are absorbed by a compound, causing electrons to move from their ground state to a higher energy excited state. By measuring the amount of light leaving or transmitted from a sample and comparing it to the amount of light that entered, so comparing what you started with to what you ended up with at the end, you can find the amount of light that was absorbed by the sample. You can use a spectrophotometer to do this. By knowing the amount of light absorbed, one can determine the concentration of a colored substance within a solution. We will look at this further in 3.13 with Beer-Lambert law. So for this one, remember that UV vis is associated with transitions in electronic energy levels, so moving from ground state to excited states. Okay, so our IDO. 2 samples of copper-2 sulfate were analyzed using UV vis, or visible light spectroscopy. Sample 1 absorbed twice as much light as sample 2. What can you deduce about the concentrations of the 2 solutions? Well, first you can say that sample 1 is twice as concentrated because it absorbs twice as much light. Looking at B, what must be true of the solutions in order to get results from this type of spectroscopy? They both have to be colored, right? Ultraviolet and visible light spectroscopy only work on colored solutions, and they have to also absorb within that spectrum, so the visible spectrum. So the light that they're absorbing must be within the visible spectrum. And then describe the types of changes that occur within the molecule during the process of UV vis spectroscopy. Well, if we go back to our notes, it says that it's associated with electronic energy levels, so transitions. So that means that electrons get excited, so the light enters the sample, the electrons get excited and move to a higher energy state. They then release light, which is being measured, as they return to a lower energy state. The light that is measured, they look at the difference between the two to figure out how much energy was actually absorbed, and they can use that to plot and determine the concentration of the solution. We will look at how we do that in a later section. Okay, we do. I want you to pause the video and answer the first one, and we'll come back and discuss that after. Okay, you should have paused the video. And so what type of spectroscopy would be responsible for the change from 1s, 2s, this first electron configuration to the second? Well, we see that this is an electronic transition, which means it must be ultraviolet visible light spectroscopy. Either one is fine, but it must be one of those two. Those are technically the same spectroscopy group. Okay, so then pause the video and answer the second one. What type of spectroscopy would be responsible for the bending of the OH bonds in water? Pause the video and answer it now. Okay, so you should have gotten that it is infrared spectroscopy, because infrared spectroscopy is responsible for identification of functional groups, and it also looks at vibrational movement, the bending and stretching of bonds. Okay, with that, please complete the you do, check your work, and thank you for listening.